Hello everyone. In this video, I am to briefly go over a model I ran in a previous video, specifically the cross-lagged actor-partner interdependence model, and then we will shift over into a new model that will be the random intercept cross-lagged panel model. So just to start, this is where the old video left off is we had estimated this cross-lag panel model using dyadic data, looking at marital support over a 4-year period among a sample of 627 heterosexual couples from the PairFam data. So essentially what we did is we did a very traditional panel model and looked at actor and partner effects of support over time. And what we had found was this data, or this model fit the data just exceptionally poorly. In no way, shape, and form is this an appropriate model. And through revising the model, we eventually figured out that the effects from very early on in the study at wave 2 and at wave 3 and at wave 4 all predicted variance in wave 5. So that means there was a fairly consistent pattern where, for example, men who were their values at wave 5 of how supportive they believed that their wives were influenced not just by their values at the previous wave, at wave 4, but also wave 3, wave 2. And that is not something we would expect. Why would we expect, for example, something that happened in 2020, for example, um, to influence something that's happening in 2024, despite that same variable being collected at 2021, 2022, and 2023. So it's a little weird for those findings to be there. Again, not COVID withstanding. So that led me to think about what could potentially be influencing these associations. It doesn't make sense that there are these lagged relationships where something that's happening again in 2020 is influential in 2024, despite those repeated measures in between. So to me, that signals that there's a confounding variable. There's something there that's acting on both of those variables that could potentially be an explanation for why those associations actually exist. And so what we've done, or what I've done more specifically, and what I'm going to go through with you is I believe and I hypothesize that there would be a kind of a stable or trait-like aspect to that relationship. For those who have been in long-standing romantic relationships, there is an aspect of stability. You can predict how your partner is going to behave in a lot of situations. And so that's going to be a trait-like component. But then people are also not robots. They are not these well-oiled machines that consistently work in the exact same way. There's going to be fluctuations and deviations from that tendency, from that average. And so, again, my hypothesis is that there are all these residual effects that we found because we didn't measure that person's general tendency to perceive their partner as supportive. So that's what we are going to do here. So again, this is the cross-lagged panel model that we did in the previous video. Again, the fit is absolutely abysmal. We see that there are just exceptionally strong effects, actor and partner, or actor effects more specifically, and then there's also some significant partner effects. And then when we added in those other pathways, which I will do briefly here, just to refresh those of you who did not watch the previous videos when we did, oops, that's the wrong one. We want to do that only on the actor effects. And so we'll do that in 3 and we'll do that on 2. And then we also want to do that for women. And we'll do 3 and we'll do 2. And then male support, on male support, we also need to add in A2 here as well. And the same thing for female support. And I believe this perfectly recreates the model from the previous video. Yeah, so now once we've added in all of those effects, the model fits beautifully. Doesn't make any sense, but it fits beautifully. And you'll see these are the effects that I was talking about. That male support at wave 3 and at wave 4 are pretty much having the exact same influence support at wave 5, which again doesn't make much sense. So although wave 2 is quite a bit smaller, it is still significant. So again, when we found this exact same pattern among women, where they have two very identical effects and then also a distal effect. So again, what we're going to do is we're going to move over to this random intercept cross-lagged actor-partner interdependence model, where we're going to tease out a person's stable characteristic in terms of their perceptions of their partner being supportive or not, from individual deviations or fluctuations from that general tendency. So I will minimize this, and we will move over to the random intercept actor cross-lag actor-partner interdependence model, which is quite a mouthful. All right, so here, everything from here is the exact same as in the previous video, so I'm not going to spend a whole lot of time going over it, but here is the title. Actually, I should probably update that for random intercept. Here's our data file. Here's our variables that are in that data file. And here are the 8 variables that we are going to use in our analysis. I would expect that marital support is not a normally distributed variable, that the residuals of marital support are likely to be non-normal. So I am using robust maximum likelihood, MLR, which employs a Yuan and Bentler correction factor, which adjusts the standard errors and the chi-square statistic to address non-normality. In this analysis, you could also do MLM, which has the Satora-Bentler correction. The reason I have MLR is simply because that can handle missing data, whereas in MLM, you need complete data, which I have in this demonstration, but I don't want to model MLM because generally, I would probably only use that following like multiple imputation because we never really have complete data in the social sciences. So I just generally don't use it, and the default is MLR. One difference is that you will see model equals no covariances. You could also do model equals no cove. That's the same thing. And essentially what that does is it suppresses that Mplus default of correlating all of your exogenous variables. So all of your independent variables, Mplus automatically covaries even if you don't request so in the syntax. So in like a multiple regression, for example, you may or may not recall that all of your exogenous predictors are actually covariated with one another, and you don't have to specify that in SPSS or even in Mplus or many other softwares because your program automatically does it for you. And in this analysis, we do not want that to happen because Mplus will insert a couple of covariances that we do not want in there and that don't make a whole lot of theoretical sense. All right, so to specify the random intercept cross-lagged actor-partner interdependence model, there are a couple of ways we can do it. I will show you one way that I think is a little more cumbersome in terms of syntax, but I will also briefly type in the other way. So the first way is specifying a latent variable. So again, I mentioned that we are going to be teasing out a person's stable trait-like perception of their partner being supportive or not over the course of 4 years. There's going to be some, again, stability around that. And so that's what we're going to estimate with the random intercept, right? And so what we're going to do is we're going to specify, I'm using 4 waves of data. You can do this with 3 waves. You cannot do this with 2 waves because your model would be under-identified. And you just don't have enough information to go around to estimate all the things that you are trying to estimate. So we have RI_M. So this is the random intercept for males, and the by statement in Mplus indicates a latent variable. An on statement is a regression, and a with is a covariance. And so by default, Mplus, whenever you use a by statement, is going to automatically fix that first loading to be 1. That's what's called the marker method of estimation. So if you're familiar with confirmatory factor analysis, this is, you've probably seen this in your output that you'll see, you'll look in your factor loading matrix or your factor loading output, and you'll see that 1 is going to be labeled as 1, and then in your unstandardized, I should be more specific, it's going to be labeled as 1, and then everything else is going to be, 1.40 and 9.98 and whatever other factor loadings you get. But that first one is always 1, and that's because the marker method is the default, I believe, in pretty much every SEM application. I know it's the default in Levant as well. So we need to override that default. And so we're going to use what's called the standardized method of estimation. So because latent variables are these unmeasured things that we believe to theoretically exist, we need to pin them down in some way, shape, and form. And so how do when we have observed variables, what do we have for them? We have means and we have variances. And so we need to do that same thing with a latent variable. We need to give it a mean and we need to give it a variance. And so when you use the marker method by fixing that factor loading to 0 or to 1, you actually also fix the that item intercept. You constrain that to be 0, and that's actually what gives your latent factor the mean and your variance. So you can estimate it, and so we can now take this very nebulous, kind of amorphous theoretical idea that isn't in our data file and actually make it a little bit more concrete, something that we can actually estimate, all right? And so in the standardized method, in contrast to the marker method, we are just going to constrain the variance of the latent variable to be 1, and we are going to set the mean to be 0. So this is just kind of like creating a z-score with your variables. So now negative values have an interpretation. All right, so the mean of the latent variable is 0. All right, so we're going to do that for both men and for women. All right, so as we think about kind of theoretically the idea of a stable trait-like feature over time. So when we think about that, we think about, it being kind of the same over an extended period of time, in our case, 4 years. And so what do we have to do in order to kind of create that stability? We have to use these value labels. I chose A1 to constrain the factor loadings to be equal across time. All right, and you do that for men and you do that for women. Because if you don't constrain these and they're allowed to vary, and you have a variable, let's say the loading is, 0.90 here and 0.85 here and, 0.80 here and 0.75 here. Well, that's not a stable estimate. That's actually, you've encountered a growth model. All right. And so if there's differential associations over time, then this is the incorrect model to use. But if we theoretically believe that people have this underlying stable trait on the construct of interest, and there's also going to be deviations from that, then we need to measure it as such. And to ascertain that stableness, as I'll call it, we have to fix everything to be equal. All right, so we do that for men and we do that for women. All right, and so you'll notice I have different value labels because I think marital research over the last 40, 50, 60 years indicates that marriage is very different for men and women. There's a lot of similarities, but it's very, very different. And it's particularly different around what marital support is and how it's experienced. And so we don't want to constrain male and female partners to have the same level of stable trait-like perceptions of marital support over time. We want to allow them to be at least a little bit different. All right. And so that's what we're doing up to this point. So that's this first this first kind of section of syntax. And then I've also mentioned how in this example, we're pinning down the latent variable to be one for the variance as well as the standard deviation, since the standard deviation is the square root of the variance. And what's the square root of one? It's one. So both your variance and your standard deviations are one for your random intercepts, your stable trait-like features. All right, and then we're going to correlate them with one another because we're probably going to expect that males' trait-like perceptions of marital support is probably going to be correlated with females' trait-like perceptions of marital support. The way I'm kind of thinking about this theoretically is probably more like attachment. We have people have a stable, relatively stable attachment style in their relationship, and that's going to govern how they perceive and interpret others' behavior. And so that's kind of how I'm thinking about this. If the idea or if the concept of trait-like and stable aren't really connecting to the concepts of marital support, that's another way to kind of think about it, to wrap your head around these types of associations. All right. And so alternatively, I'm not going to estimate it, but I'll briefly write out the syntax, is the second way of estimating this. And so we'll do random intercept for males, random intercept for females. And the syntax is going to be much more compact. And so we'll still do our by statements for both. All right. And I'm just going to be lazy and I'm going to do some copying and pasting. And hopefully it doesn't go too wrong on me. And what we're going to do is, rather than allowing the factor loadings to vary, because they're allowed to vary here, they're just constrained to equality. So you picture it like being 4 kids, and they all get to do an activity, right? They all get to play a video game or something like that. But they all have to play the exact same video game and they have to agree on that. So that's a nice metaphor to understand what's going on in this first model. But up here, or down here, I should say, is we're going to fix everything to 1, all of these factor loadings. So they're not free to estimate. They're not free to vary. You're not letting the kids decide among themselves what video game they're going to play. You're coming in as a parent and you're going to say, you're going to play this video game that's going to increase your reading ability or whatever it is. You're going to play this non-violent video game that are just way less fun. Okay, so you're coming in, you're dictating the amount of influence that their stable trait-like behavior has. All right, so we'll fit this model, and this is what the syntax looks like. And so if you were operationalizing your random intercept this way, you could get rid of all of this. Whoops, I have to highlight all of that. All of this syntax can be gone. You no longer need these restrictions on the latent means, or the latent factors, I should say, those means and those variances. Right, but this would be the syntax for it. And this choice is, I think, is largely theoretical. If you talk to Todd Little and his colleagues, Danny Osborne, down in Australia, they are a big advocate for this approach, where you're allowing those loadings to be freely estimated. But if you talk to Ellen Hamaker and her colleagues, she's actually one of the core developers of of the random intercept cross-leg Panna model, not necessarily in the context of dyadic data, but she wrote the seminal psych methods, I believe, article on all the things that are wrong with the cross-lag panel model and advocated for us to do these types of analyses that we're doing here today. All right, and so I am preferential to Todd Little's perspective, simply because I I believe, when we kind of taking this to like a measurement arena, when we create a sum score, we're actually imposing a factor model. And so we're actually constraining the factor loadings on the latent variable, which is your construct to be one for every single item. So if you have a 3-item depression measure, you have sadness, you have sleeplessness, you have suicidal ideation. All of those loadings are fixed to 1, and your latent variable is depressive symptoms. All right. And so to me, that's problematic because I throw that into, Mplus. I fit that model, I constrain all of those loadings to be equal, and I have terrible model data fit. But when I allow those loadings to be free, then the model really cooperates quite well, and it's very, very well behaved. So I'm just kind of borrowing some of that logic, and I don't really want to constrain the extent to which there is trait-like similarities over time. Rather, I want the data to really speak to me and allow that to come out rather than being imposed on it. Because I actually believe we need to learn from our data, in contrast to many people who think that we just run models and we don't consult our data whatsoever. I think that's actually highly problematic, but that's another rant for another day. All right. So now that we have talked about the specification of the random intercept and the covariance between them, now we will get into the within portion part of the model. So now these next 8 lines of syntax, what they are doing is they are utilizing what's called phantom variables in order to disaggregate the individual deviations over time from the trait-like intercept or that random intercept. And so what we're doing is we're creating new variables and just simply creating 8 new factors. And so this is my new variable. It's going to be W underscore then M sup 2. So what that is it's within and then male sup 2. And so I specify that using a by statement. So don't use an on statement here, use a by statement because that's what creates the new variable. And then I use the observed indicator that's actually in my data file as the sole and only indicator. And to identify it, I constrain that factor loading to be 1. All right. And you're going to do that for every single one. So you're going to go through however many waves of data you have. You are going to create these phantom variables. And the information located in these phantom variables are going to be the deviations at that wave for that person compared to their trait, their random intercept or their trait-like experience. So let's say over the course, I'm picking numbers just out of the clear blue sky, someone has a kind of an average of, at 8 on marital support. But let's say they're at time 1, they had just gotten married. They're newlyweds. So they were actually at a 10. A 10 is, let's say, the highest you can get, 0 to 10 scale. So they're going to be 2 units above their average. So they're going to have a positive deviation. And then at other points in the study, they're going to have negative deviations. They might be below their general tendency. Okay. And so that's what these variables capture. We want to know to what extent do people deviate from their general tendency in marital support, and what are the implications for their partners? So that's what these 8 lines of syntax capture. we create those within person deviation variables using phantom variables for men and for women. And then this is where things get actually quite fun. So what we're doing now is we're expressing this essentially the same model. Think back to our cross-lag panel I just pulled back up, getting rid of these modifications. We are looking at essentially the same associations, but at a different level. In this previous model that we ran, we are smushing together that stable trait-like variance and mean with the means and the variances and the deviations from that stable trait-like characteristic, and we're only getting between person effects. So when we think about interpreting cross-lag panel models, we're always talking about our population, our sample in general. So individuals who have higher levels of support at wave 2 also tend to have higher levels of support at wave 3, right? So we're focusing on between person or between dyad effects in the cross-lag panel model. But here we are looking at individual deviations from those effects. All right, and so that's what we're capturing here. So the syntax looks almost identical. All right, so wave 5 for males with in-person support on wave 5 for wave 4 for males and wave 4 for females. So this is an actor effect right here. This is going to be actor effect, and then this will be a partner effect. And you can copy those all down the line as long as if the M here and the M here match, then it's an actor effect. If the F here and the F here match, then it's an actor effect. But if they're mismatched, then they're partner effects. Right? But essentially, it's the same syntax as before, but now we've just pulled out that general tendency for people for people's perceptions of marital support. And what you will notice here is I've imposed some equality constraints using these labels. So you don't have to. I'm just going to kind of walk you through kind of what it looks like. And so we'll actually go over that here in a moment. But essentially, what the idea is that actor effect for males between wave 4 and wave 5, I am telling it you have to be equal to that same effect in females. Right? And so what I'm really assessing here is kind of moderation. And if these effects harm the model, then we have gender differences, that this within person stability effects are different for males and for females. It means men who are more positively deviated from their mean in terms of support are at wave 4 are going to be more positively deviated from their general tendency to view their partner as supportive at wave 5, and that's significantly stronger than women, for example, right? And what I've also done in that's within kind of between two waves. That's kind of in one set of analyses. I'm constraining these actor effects to be the same. I'll type that in here. Partner. But what I'm also so that's all within one wave. But so I could change the syntax down below, and I could allow there to be differences between the waves. So the amount of change between time 2 and time 3, or I shouldn't say change, the actor effect between time 2 and time 3 for men and for women is going to be identical to the actor effect between time 3 and time 4, and for time 4 and time 5. So as you can see, I'm placing a lot of restrictions on this model. I'm allowing those actor effects to be estimated, But again, that's the same example as before. I'm telling those kids that they have to go, they can go play video games, but they have to decide amongst themselves what video games they want to play. All right. And so it might be that this is actually not a great fitting model, and I'll show you how to adjust for that and some other things that you can do, because really this is where the fun is. This is where you're kind of on a playground of sorts, because you can create all sorts of different model constraints. You can compare, you can constrain actor effects to be equal to partner effects and see what that does. You could constrain, if you really wanted to, an actor effect for males between time 4 and time 5 to be the same as an actor effect for females between wave 2 and wave 3. Why you would want to do that, I don't think there's probably a good reason, but you can. Right. And then down here, I've likewise created some covariances where I am correlating those with in-person deviations across dyad members within the same wave. So stated another way, male deviations from their general tendency to view their partner as supportive, I'm believing that's going to be correlated with women's deviations, their partners' deviations from their general tendency to be supportive. All right. And then in order to get all these fancy smancy associations, these within person effects, we have to fix the measurement error or the residuals of these observed variables to be 0. All right. And so essentially what we're doing there is typically we believe that all dependent variables are measured with some form of error. And so we give them a residual variance. But what we're doing here is that we're actually pushing that assumption into the within person portion of the model. All right, so kind of view it as, we have these association, we have this information that each variable holds. So the information that male support at wave 2 holds is now being pulled in 2 different directions. Some of it's shooting up to the latent variable, and it's that between person stable trait-like tendencies over the course of the study. So that's some of it. And then the other half is getting pulled down into this residual, into this phantom variable, I should say, this within person effect. And so in order for that information to be pushed up, or I guess pulled up would probably be more appropriate, and pushed down, we have to fix those variances to be 0 in order for that to happen. Otherwise, we don't know where that information is going, and there's not a clear direction, and it just creates a whole lot of confusion. Right. So now that I have talked way too much for far too long without actually running anything, we will jump into the model. And again, this is standard output for mod indices, stamp stat, SCDYX, residual. I might even add tech1 in just to label parameters in case we ever run into errors, but we should be fairly good to go here. All right, so you'll get some warnings, and that's only because I have some annotated or commented out text that describes kind of what I'm doing. So you can ignore that. That has no impact on the model. Again, I have complete data, so I'm not really paying attention a whole lot here, especially given the kind of more didactic nature of this video. If I was a substantive researcher and this was trying to answer a research question, I would certainly be more interested, but here, not at all. All right, so before, I'm just actually going to pan back over to that cross-slide panel model and just look at this. That's the output that I accidentally modified. Let me make these corrections real quick and rerun the model so we can just, again, get a sense of the fit statistic difference between these models, because they're actually nested within one another. If you just if you fix those the factor loadings to be 0, then you get this answer all over again. All right. So we'll scroll down to fit, and just an unbelievably terrible model, not even close to fitting well. And here now we are doing so much better. All right, we have more degrees of freedom, and our chi-square is 9 times or 8 times lower. So doing well in that respect. Our MSCA is low. It's got a fairly tight confidence interval around it. The probability is below 0.05 is 93%, which is good. That's a well accepted cutoff, despite no fit statistic actually having a set cutoff. CFI and TLI are doing brilliantly. We have SRMR, which again, I whine and complain about this one. I like this statistic a lot, but doesn't tell us a whole lot. It's actually higher than it typically is. So we'll kind of ignore all those, but taking everything together, this is a wonderful fitting model. All right, so model results. So here are the unstandardized loadings. This are within person effects, and because they're constrained to be 1, there is no standard error, there is no test statistic. We are telling that parameter, this is who you are, so there's not really an estimate involved, so there's not a standard error involved. All right, here's where things get a little interesting. Is we have the same exact effects between all 3. There's 4 waves across all 3 differences between waves, all between wave 2 and 3, 3 and 4, 4 and 5. They're all fixed to be identical. And so a good way to check your syntax is, are all of these results identical? So 6, 4, 6, 4, 6, 4, 6, 4, 6, 4, 6, 4, we're good to go on the actor effects. Partner effects, 1.012, 012, 012, 012, we're good to go on the partner effects. All right. Now we go down to the covariances, all of them 0.30, we're good to go there. And we check our means and our variances. They're 0 because that's what we told the model you're going to do. Same thing with variances. And then we also have an indicator of variance for our within person effects at the first wave of data collection. I guess here in the second wave of data collection, that's the variance for that within person effect. Within males, the variance is 2.193, and for females, it's 2.361. All right. And so earlier I had indicated the model, we suppressed that default of Mplus to automatically covary our independent variables. You'll see here, these, because these are on variances, they would have been covaried. So we would have had covariation within M sub 2 with the random intercept for male and females, and that just doesn't make any sense. Why would a male's deviation from their stable trait-like perceptions of marital quality over time be correlated with the actual deviation at wave 2? Doesn't make any sense. So that's what we suppressed by using the no cove option. And then obviously we have residual variances. So we have at waves 3, 4, and 5 residuals, because they are being predicted even at that within person level. And so as you can see, they're all significant. And this might seem a little weird that it's working this way, but this is honestly no different than standard structural equation modeling, standard multiple regression even, because the assumptions that we make about our X variables is that their distributions are fixed and known, and they're measured without error. They're perfectly reliable. And so that's the assumption that we're kind of making here with these guys. But on the dependent variable side, we allow there to be error. We recognize there's fuzz. We recognize our model is only so good at accounting for variation or between person differences. Oops. And so we actually allow those models to have residual variances. We're just, again, pushing that assumption from multiple regression down into the within person effects in this model. All right, so we'll move down to standardized. So as you can see, the effects are fairly small. They're all non-significant. And you will see a little bit of variation. All right, so it's not all 0.074. You'll see 0.067, and that's what standardized estimates do. They will vary a little bit on you. So that's why I tend to use the unstandardized estimates when doing these types of models, although I try to report both. And then we also have our covariances. All right. So now that we have kind of estimated the model, what we can do now, and I think this is again where it comes more of a playground, is we can begin relaxing these constraints, and then these are nested models, and so we can just do chi-square difference tests. And so let's just allow everything to be freely estimated between waves. So we'll make everything a little bit more free. All right. So what I've done here is the actor and partner effects within a given wave. So the effect from time 2 to time 3 is still the same for males and females. That actor effect and those partner effects are still the same for males and females. So essentially I'm still saying males and females have the same effect on their own outcome, and they have the same level of mutual influence. But what I'm allowing the model to do now is between waves, I'm allowing those to be freed. So the actor effect between wave 2 and wave 3 does not have to be the same as the actor effect between wave 4 and wave 5, which was the case in the previous model that I ran when I had everything labeled as a B. So we're going to see what that does and to see if that improves our model data fit. I'm not going to go through the formal chi-square difference tests. The best way to do it is you just take your degrees of freedom from you just subtract the degrees of freedom between the two models. You subtract the chi-square statistic from both models, and then you're going to end up with a different score for both. And so you'll just have to look up on there's an online calculators all over the place. If you have a chi-square of I just know a couple of them off the top of my head, but let's say you have 1 degree of freedom between the two models, you impose 1 restriction. And so your chi-square goes down by 7, for example, then it is a significant difference. Your model is harmed, and placing that restriction in the model is bad for the model. So you need to go back in and go back to your model and put it back in, right? But if it's, let's say 2, then it's non-significant because that critical value is 3.84, right? So again, I'm not going to go through and do that. I might eyeball a few things, but you can do those formal tests in a very easy manner. So let's go ahead and run this. All right. So we'll scroll down to our fit statistics. And so we see that we gained some degrees of freedom. Or we lost some degrees of freedom because now we are freely estimating more things. We are allowing parameters allowing them to be free to be you and me. We're allowing them to have individual identities when we weren't before. We are telling them who they were. And so the fit, the chi-square tended to be a little bit better, but I'm not seeing a whole lot of difference in fit. The CFI and the TLI are nearly identical. RMSEA, where'd you go? Nearly identical. It went up just a tiny bit by 0.03, I think, or maybe 0.05. SRMR went down a little bit. But all in all, freeing up these parameters does not appear to have had a kind of a positive impact on the model. And so I would probably add those constraints back in to get a more parsimonious model. At least if I stop there, that might be an option. But what can we do next? Well, what we can do is maybe husbands and wives, they don't, they might have weaker, one might have stronger or weaker actor effects. So let's just throw on a 0 to the partner effects and what this is going to do. Since this and this no longer match, the actor effects are now going to be freely estimated. You can get rid of the label, or you can just make it the label unequal. And so now we'll be estimating three more parameters, right? So our degrees of freedom should go down by 3. All right. All right, we are at 18 and now we are at 15. All right, and so our chi-square before was around 31, something like that. So 3 degrees of freedom, our chi-square did not meaningfully change. So freeing up those parameters did not help our model. And I recognize I'm doing this a little bit backwards. Typically, we freely estimate everything and then we gradually restrict, but I'm actually doing it I'm doing it backwards. We're in the opposite direction, so I can show you the path constraints. So if you are getting that, thinking about this looks different, that is potentially why. All right, so that, didn't really help us. All right, so maybe we want to, maybe free up those partner effects. All right, so let's do that. And so now none of the value labels are going to correspond to one another. That means all of the actor and partner effects for the men and women, they are going to be freely estimated across all the waves. So there are no constraints placed on those actor and partner effects. The only constraints that remain are on the covariances. So we'll go ahead and we'll estimate this model. And so again, we gain 3 more degrees of freedom since there are 3 more paths being estimated. And if you have questions about why is it 3, because we actually freely estimated 3 paths beforehand, they were just constrained to equality, but they're still considered freely estimated. Now we're allowing all those paths to be different. That's why the degrees of freedom change is half of what it would have been had we had fixed the parameters to be a specific value, like fixing them to be 1 or something. But that commonly confuses people. Why we get 3 degrees of freedom back when now we're estimating 6 freely estimated parameters. It's really because they were freely estimated before, but they were just constrained to equality. All right, so our RMSEA shot up, or it's starting to get a little bit bigger. So that's telling us maybe we're going in the wrong direction, but also the RMSEA does worse and worse as degrees of freedom get smaller. So take that with a grain of salt. TLI is about the same. CFI is about the same. SRMR is about the same. Again, model fit doesn't seem to be harmed at all by freely estimating all of these parameters. And so now what you're seeing is we don't really have any within person effects. So, when husbands and wives are deviated from their average, it doesn't positively or negatively influence the other person's deviations. So the more men are more supportive than they usually are, that doesn't necessarily predict women being more supportive than they usually are in the following wave. All right, so those partner effects are 0. And men who perceive their spouse to be more supportive at wave 2, that doesn't predict them perceiving their spouse to be more supportive than they usually are at wave 3. So they don't even predict their own deviations. So we're not seeing a whole lot of significance at this level. So the last thing to do is to freely estimate these these covariances. And again, you can delete them. I just add more values to them because I find it to be easier, or you could comment them out, but then you have to add in a comma, and then if you bring them back in, then I invariably forget one of the semicolons, and then Mplus yells at me. So I find just modifying the labels to be the easiest, as long as you can keep track of them. All right, so this will be our final model that we're actually going to run. And so we have a brilliant model. We can see that freely estimating these parameters will greatly increase the model fit. Our chi-squares are now non-significant. Both CFI and TLA shot back up. RMSEA shot way back down. It was at 0.52 or 0.53 in the previous model. And SRMR, it went up a little bit, but again, we're going to kind of ignore him because he's not contributing all that much. But look at what we're having now. Once we allowed the extent to which males and females correlated in their deviations from perceptions of marital support at each wave, we are now getting some significance, right? And so we have a significant effect here, and we also have a significant, borderline significant effect here. All right, so how we would interpret this, and this is a partner effect, would be that the more females deviate positively from their tendency to be perceive their partner as supportive, is associated with a 1.1 unit decrease in men's deviation generally in their tendency to be supportive. So they perceive their spouse or their partner, their wife, to be they're less supportive than they usually are, right? And so that might seem kind of counterintuitive. Well, if women perceive their partners to be more supportive than they usually are, why would men kind of feel the opposite a year later? Well, I'm not going to dive into a huge theoretical discussion, but there could be, power imbalances. It could be that it's early on in the study and there's something going on in the world, for example, like a COVID. There could be some possible explanations for these deviations, but they do emerge. All right. And so when we think back to our constraining the actor and partner effects to be equal, well, here we can say, well, that was a terrible idea. I don't know, why did the model pick that up? Well, it's because we had those residual covariances constrained to be equal across those waves, and that was systematically changing the associations due to SEM being a system of equations type of analysis. And so be careful and be mindful and tread lightly when you are doing these model comparisons. And it's always best to, again, think about the associations, think about your data, and think about the extent to which how mucking around in one area of the model can actually influence other areas of the model, because again, it's simultaneous estimation of equations. So if you tinker around in one area, you tinker around in every other area. There's ripple effects that you will see. Some are big ripples that turn into tidal waves and tsunamis. Others are little ripples that you don't even see a little ways out. It's kind of analogous to working with families. So if you change the child's behavior, mom and dad's behavior is going to change with it. So it's the same type of thing within SEM. And you're going to see sometimes you're going to have positive effects where positive deviations lead to more positive deviations. And sometimes you're going to have negative effects where, positive deviations lead to negative deviations. or you can even have mixed effects, where you get an actor effect could be negative and a partner effect could be positive, or vice versa. So all of those are completely normal to see in your model. The other thing I want to highlight before ending the video is you will notice that as we've allowed these, or you may have noticed, I should say, allowed these parameters to be freely estimated, you'll notice these standard errors have been going up and up and up and up. In our first model where everything was restricted, these standard errors were around 0.2, 0.3, I think somewhere in there. They weren't very big. But as we're freely estimating these models, we're getting more and more fuzz around our parameter estimates. So it's actually not uncommon to have a standardized beta weight of 0.50, but the standard error be 0.40 and it's not significant. It's because there's just so much variability around that. And that's a normative part in the model. So if you have a reviewer or an advisor or somebody else saying, what's the point of this? Because, your standard errors are so large. Well, that's a normative part of the process. And by making models more and more complex, we are, of course, we're going to have more fuzz. We're going to be less confident about these are the population parameters that are occurring. Right. So that is perfectly normal. And Jerome Mulder, he's a colleague of Ellen Hammacher's, has a wonderful GitHub page where he talks all about about these types of things. So I highly recommend, if you're interested in this type of model, to see his GitHub. I believe he spells, I think it's Jerome, Gerone, and then Mulder. I am probably butchering his first name. I think he spells it a little bit differently. So don't quote me on the exact spelling, but again, he is wonderful in terms of the resources that he provides. Hopefully this has been helpful, and I will see you all in another video.